This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 1, Hydronic Piping and the Pump System Operating Point. A pump does not deliver a flow you choose. It delivers wherever its own falling head curve crosses the piping's rising system curve. That crossing is the operating point. We'll read both curves, see why a closed loop forces the pump head to equal the loop friction, and compute the water horsepower and brake power right at that point. For pump fundamentals themselves, the TFS course Week 4 is the primer. Concept 1. 2 curves, 1 point. Sizing a hydronic pump overlays 2 facts about the same water. The pump curve is the head the pump can produce, and it falls as flow rises. The handbook plots head, power, efficiency, and NPSH against flow. The system curve is the head the piping demands, and it rises with flow, roughly as flow squared. The pump can only run where those meet. 1 flow, 1 head. Concept 2. The operating point on the plot. The blue pump curve falls. The orange system curve rises. Left of the crossing, the pump makes more head than the loop needs, so flow speeds up. Right of it, the loop needs more than the pump makes, so flow decays. Only at the crossing do supply and demand balance. Drop the point down for the delivered flow and across for the delivered head. This same figure sets up parallel and series pumping later. Setup. The system curve. This one is a concept, not a boxed handbook equation. Turbulent pipe friction scales with velocity squared, so for one fixed layout, the required head tracks flow squared, a parabola through the origin, for a closed loop with no net lift. Change the flow, and the operating point moves along that parabola. Cut flow to 80%, and the same loop needs only 64% of the head. Slowing the pump slides the point down the same curve, to a lower flow and a lower head. Setup. The heads balance. Write the mechanical energy equation in heads across the pump and loop. Go all the way around a closed loop, and you return to the same state, so pressure, velocity, and elevation all cancel, leaving pump head equal to loss head. The pump adds exactly the head that friction removes, and that is why the operating point must sit on both curves at once. The pump's head is its shaft work per unit weight of fluid. Setup. Power and givens. For water near room temperature, the water horsepower, the theoretical power to circulate the flow, is flow times head over 3960 when head is in feet, or flow times pressure over 1714 when it's in psi. Brake power divides that by pump efficiency, with specific gravity carried along for anything but water. Our givens. The operating point reads 440 gallons per minute at 90 feet of head, water, efficiency 0.8. Solve. Read the crossing. 440 gallons per minute at 90 feet. Water horsepower is 440 times 90 over 3960, 10 horsepower. Cross-check with the pressure form. 90 feet of water is 39 psi, and 440 times 39 over 1714 is the same 10. Brake power is that over efficiency, 12.5. The motor covers 12.5 of shaft demand. The water only ever received 10. The missing 2.5 went to pump losses. Traps. 5 ways this bites. 1. The pump runs only where both curves cross. Read the point off the intersection, not the shutoff head. 2. Parallel pumps add flow at a given head. Series pumps add head at a given flow. Swap them and the point and the power are both wrong. 3. The 3960 form wants head in feet. The 1714 form wants pressure in psi. Mix them and you're off by a factor of 2.31. 4. Water power is not brake power. The shaft must supply water power divided by efficiency. 5. A closed loop system curve passes through the origin. An open loop carrying static lift starts above 0. Quick recall. The operating point is where the pump curve meets the system curve. 1 flow, 1 head. The pump curve plots head, power, efficiency, and NPSH against flow. The system curve is a parabola in flow squared, a concept the handbook doesn't box. Around a closed loop, the pump head equals the loss head. Water horsepower is flow times head over 3960, or flow times pressure over 1714. Brake power is that over efficiency. Golden rule. The pump lands where its falling curve meets the loop's rising parabola. Nowhere else. Next up, Lesson 2, Cooling Towers and Fluid Coolers. Now that we've moved the water around the loop, we reject its heat to the atmosphere. We'll define range and approach as labeled water and wet bulb temperature differences, work the makeup and blowdown balance, and meet the exam's signature ton trap. A cooling tower ton is 15,000 BTU per hour, not the 12,000 of a refrigeration ton. Everything's at prepengine.com. Cheat sheet, work solution, and a quiz attached here.
The full study guide with every equation and common exam trap is free at peprepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.